Today's lesson is about triangle proportionality. So in your book, we are combining lesson 20.2 and 20.3 together. So let's do a quick review. Proportions. If the given objects are the same, as in congruent, then the scale factor is 1 to 1. Okay, so reads as 1 to 1. Second review, scale factor. If the pre-image is twice the size as the image, then the scale factor is 2 to 1. Okay, so the 2 is talking about the first object, and the 1 is talking about the second object. Okay, so if you're thinking about, well, it should be 1 to 2, so side note, if scale factor is 1 to 2, then the pre is half the size. Okay, half the size the image. All right. All right, next is base angles theorem. So for base angles theorem, it's when two legs of a triangle are congruent, and by this part of the statement, you should know when you have two legs that are the same, then it is safe to assume that you would have what it's called an isosceles triangle. So we're talking about isosceles triangles here. Then the two angles opposite from the legs are also congruent. So I have a triangle here. Let's label it triangle ABC. And as you can see by the marking, side AB is congruent to BC. So according to this theorem, that the opposite angle from BC, which is angle A, and the opposite angle from side BA is angle C. So because the legs are congruent, right, it's a double tick mark on each side, that means both are the same thing, then that makes the two angles, which means angle A and angle C, to be congruent. All right, so let's write that out. If AB is congruent to BC, then the measurement of angle A is equal to the measurement of angle C because of base angles theorem. Okay, so not only the angles are congruent, but the measurement are the same as well. So for base angles theorem, the reverse statement is also true, which is called converse base angles theorem, which is basically saying that the reverse statement of base angles theorem is also true. So what is the reverse statement? We basically do it in reverse. So basically, if you have triangle DEF here, and the bottom two angles, which means the base angles, and they are the same measurement, then the leg opposite of each one is also going to be congruent. That's basically what the converse base angles theorem is saying. All right, triangle proportionality. So this is also a theorem. Let me fix that. So when you have a line drawn parallel to one side of a triangle that divides the two sides proportionally. All right, I have a triangle here. So let's say I drew a line right here, as best as you can as well. And as you can see that this line right here is parallel to the one at the bottom. All right. So I'm going to label the triangles A, B, C, D, E, just going down the line here. And I am marking angle A to be congruent with angle CBD. And BD is 20, AE is 35. Again, the diagram is not drawn to scale. And let's say AB is 12 and CB is X. So that means from here to here, the measurement is unknown and we are looking for it. So what do we know about this triangle? So we do know that angle A is congruent to angle B, okay, which is by corresponding angles, all right? And we do know that segment BD is parallel to segment AE, okay, by this one's given, right, because it's been provided for you through the diagram. So we could do a comparison, and we want to compare small triangle over big triangle, all right? And so what is it that we're trying to compare? We're looking for some kind of proportionality, so we need to set up a proportion, okay? And the way we set up that proportion is because we're looking for X here, and that belongs to segment BC, and that is in the small triangle. And if we're comparing it to the big triangle is not just this part right here. The big triangle is actually the whole thing from A to C, okay? And the smaller triangle is from B to C, all right? So make sure that you could differentiate the two triangles that's there, all right? So big triangle is AC. And because we have BD and AE, we also want to use those information to help us with the proportion. So now we get to plug in information. BC is X, and AC is AB plus BC, which is AB plus BC. So if AB is 12 and BC is X, and it's the whole thing, so then we can write it as 12 plus X. And make sure you put that in parentheses, all right? All right, BD is 20, AE is 35, and look, we have a proportion. We can now multiply, so we're going to cross multiply, and we get 35 times X equals 20 times 12 plus X. All right, so 35 times X is going to give us 35X, and 20 times X, we're going to distribute that. So 20 times 12 is 240. 20 times X is 20X. All right, and solve for X, just like you normally would in solving equation. We would need to subtract 20X to both sides. And 20X minus 20X is going to give us 0. And we're left with 240 on the right-hand side. 35X minus 20X, that is going to give us not 10X, but it's 15X. Very good. So then we solve for X, which means we need to divide both sides by 15. 15 divided by 15 is 1, which leaves us with just X. 240 divided by 15, you guessed it right, it is 16. So X is 16, but if you look back to your diagram, X is representing segment BC, all right? So that means BC is equal to 16. All right, next is the angle bisector theorem. So this is saying that if a ray or a segment bisects an angle of a triangle, then it divides the opposite side into segments proportional to the lengths of the other two sides. Here I have a triangle BAC, and let's say there is a ray coming out from angle A, and we're going to label this point as point D, where the ray intersects with segment BC. So because the ray is an angle bisector, and bisector means it cuts it into two equal parts, so because it is cutting to angle A, then the left side of angle A is congruent with the right side of angle A. And what this does, it divides the opposite side into segments that are proportional to the lengths of the other side of the two sides. So what does this mean? It means that the ratio of the length to BD to the length of DC is equal to the ratio of AB to the length of AC. Okay, so let me highlight this. So that means BD and DC, the ratio of BD and DC is proportional to AB, which is right here, with AC, which is right here. All right, now it says proportional. Okay, so that means if you're given numbers for segment BD and DC, as well as AB and AC, and if you reduce those fractions, it would have the same scale factors. All right, here's an example. Let's say BD is X, because we don't know what that is, but we do know that DC is 12 and AB is 8 and AC is 16. So 8 and 16. So if you use the setup that I provided up there, which is BD over DC equal to AB over AC, and plug it in, so X over 12 equals 8 over 16. Now, we could simply cross multiply, so you would get 16x equals 96, and 96 comes from 8 times 12. And solve for x, so divided by 16 to both sides, and x is 6. Okay, so then that means BD is 6. All right, so that's one way. Another way is if you actually realize that AB to AC, which is 8 over 16, and if you reduce that as a fraction, it's 1/2, then you could think about, so if BD and DC is proportional to AB and AC, then that means we need to figure out a number for BD that is half of DC, right? Which means half of 12. And half of 12 would be 6. And that is exactly what we found using proportionality.